Okay, guys, thanks for being here. I'm glad to present to you my presentation. A friend of mine told me to start my presentation by asking you to do some breathing exercise and synchronize our breathing, but I'll skip that part and just move to, because we don't have time anyway. So the agenda is what is a multi-chain bridge? Why do we need a multi-chain bridge solution? How they work? And if we have time for a demo, because my time was cut for some reasons, I don't know why. So maybe we won't have time for the actual demo, but I'll do my best to go quickly through the slides, because it wouldn't make sense to actually show you a demo of something that I haven't explained first. So what is a multi-chain bridge? A multi-chain bridge is basically a way to transfer data between one chain and another. And because there is no easy way for one chain to know what happens outside of it, that's what a multi-chain bridge does. It basically allows you to send data across different chains because we need it. Why we need it? Because we already know that the world is going to be multi-chain. We won't have a single chain. We'll have multiple chains. We currently have over 1,000 active chains. So there is a need for multiple chains. So there is a need for a way to transfer data between them. Before getting to the details, we need to say that every chain or every network has their own native asset. So for example, for Ethereum, that's ETH. For Near, that's Near. For Polygon, that's Matic, and so on and so on. Now let's say that we want to transfer ETH from Ethereum to Polygon, but Polygon doesn't have ETH because ETH is the native asset of Ethereum. Then what we have is a Ether representation on Polygon, which is actually a ERC20 token on Polygon. And now the question is, how do we transfer ETH from Ethereum to Polygon? And we can break down the whole thing into two questions. The first question is, how do we verify that we have ETH on Ethereum? And the second question is, how do we verify that once the Ethereum is on Polygon, we don't actually do some kind of double spending and we end up with Ethereum on both the Ethereum network and on the Polygon network. And we will get to that a little bit later. And now the question, why? Why do we need multi-chain bridges? The first reason, and probably the most used nowadays, is that we have a lot of DeFi applications. And for example, Aave allows us to lend and borrow money. And if we are on Ethereum and we want to lend our ETH, we are going to receive, let's say, 0.5% interest a year. And now on Polygon, we have the same protocol deployed on Polygon, and they give 3% interest on our ETH instead of 0.5. So we have the incentive and the benefit to move to Polygon and lend our ETH on Polygon because we are going to receive a better interest. And that's just one of the use cases. Another use case is that on Ethereum, if you have to do a transaction, you most probably have to pay a lot of fees. Today is a good day because the fees are low on Ethereum because the congestion is not that big, but we've all seen that you can pay up to $1,000 for a transaction. So if $1 is enough for one transaction on Ethereum, with $1 you can do, let's say, 200 transactions on Polygon, which at the end will give you a better incentive to do transactions on Polygon. Now to the interesting part, how they work and why we should care about them, and how we can pick the most secure and trustless bridge. So let's consider this example that we have Arbitrum, assets on Arbitrum, and we choose Arbitrum because it's an rollup solution, and we assume that to some extent it has the full security of Ethereum, which means that it's almost as secure as possible. But then we want to have assets on Optimism for the same reasons. Optimism is fully secure, almost as secure as Ethereum. And we want to have funds there because, I don't know, they are going to do some NFT airdrop or something like that. And we can bridge our Arbitrum Ethereum to Optimism Ethereum. And for that, we are using some kind of multi-chain bridge or a cross-chain bridge. They are the same. So we are not secure because we don't rely on the network security anymore, but instead we rely on the bridge security because every bridge has their own set of verifiers. So if Arbitrum and Optimism, they rely on the Ethereum validators and verifiers, whenever we have to bridge, we rely on the bridge verifiers, which we have to be certain that is secure. And whenever I say secure, I don't mean technically secure, because technically secure means that the code is safe and everything is written as it's supposed to. But we can't know that. What we can know is if the bridge is crypto-economically secure, which means that how difficult it is to corrupt the verifiers and how easy it is to do malicious things on the bridge so people can lose funds. And whenever we talk about crypto-economic security and trustlessness, we can ask only one question, and the question is who is doing the verification and how easy it is to corrupt them. So there are several ways to verify transactions between chains. The first one is the native verification way, which is the most secure one, but it has its downsides. So how this works is basically you have chain A and chain B, and all of them have a light client embedded inside the virtual machine of the other. So in that example, chain A have a light client inside its own virtual machine of chain B, and chain B has the light client of chain A. So this means that in a real world example, this means that every transaction between chain A and chain B is verified by its own set of the set of the validators of the whole network. So the chain is as secure as the bridge is as secure as the chain is, which is the most secure way. Now the downside to this method is that you cannot generalize it because each chain has their own consensus algorithm. They have their own rules. So you have to implement a light client solution for each and every chain, which can be really expensive and not very scalable. The next solution is locally verified solution, which basically comes down to every party that's involved in the swap verifies on their own. And if there are two parties involved in the swap, this means that only the two parties have to verify the transaction, which is very quick and secure. But the downside to this is you can't apply it to all the chains. You can probably only apply it to EVM chains, which is again a huge limitation because we don't have only EVM chains. One example of such kind of breach is HOP, HOP protocol. How many of you have used HOP? Yeah, okay, cool. And another, yeah, I think that's all for this. The other way of verifying is by having an external verifier. This is the most used solution and the most used use case. So we have chain A and chain B, and we have an external verifier, which is a whole complete different node, which observes both of the networks and performs actions accordingly. Now the question is how this third-party observer or verifier can be trustless. The way they do it is by some kind of multi-signature wallets MPC wallets or some kind of oracle, because the whole problem can be seen as a subset of the oracle problem. But essentially, it all comes down to some kind of a multi-signature. And the last but not least way is the optimistically validated way. So we have, again, two chains. We have an external verifier. But the thing is that whenever you submit a transaction, we optimistically verify the transaction, but we have a challenge period. And in that challenge period, if only a single validator or watcher says, okay, that transaction is not valid, then our transaction is reversed. Otherwise, it's okay. Now, the downside to this solution is that it's not very user-friendly, because in order to have our transaction finalized, we have to wait for the challenge period. And there is one example of the Nomad breach. So you submit a transaction, the transaction is successful immediately, but you have to wait 30 minutes for the challenge period, which can be a little bit frustrating if you're in a hurry. And now, as we have the scalability dilemma, where you can have a blockchain which is scalable, decentralized, and secure at the same time, here, for the bridges, we have this dilemma, which is we can have a bridge that is generalizable, trustless, and extensible at the same time. So actually, we don't have a solution that's perfectly okay. We only have to do trade-offs and to pick the best solution for us. And here I have some applications as an example of multi-chain bridges or cross-chain bridges. Can you guess what's the common thing between all of them? Yeah. All of them were wrecked at some point. So all these 5 combined have lost around $1 billion. So we have to be extremely careful whenever we use some kind of a bridge, or we want to be a liquidity provider in such kind of bridge, because whether it's technical issue like a code issue or economically unsecure network, we have to be extremely careful. And now I think we have time for the demo. My guy who is supposed to show me the time is not there. Okay. Okay, so the demo is supposed to work for externally verified bridge, which is a bridge that has a third-party verifier, and that's a separate software that will run on the background, and it will verify transactions on one chain and submit transaction on the other chain. For the limited time that we have, I have prepared not now, but before, I have prepared a simple smart contract that is supposed to allow swapping assets from 2 EVM chains. So we'll have the same contract deployed on 2 different blockchains, and on the background we'll have a observer, verifier, or whatever that will listen to both chains and get data from one chain and publish to the other chain. Can you see? Well, yes, okay. So what we have here, how many of you are familiar with Solidity? Okay, half of the room, which is good. Okay, so we have a MPC address, which is supposed to be a multi-party computational address. But for the demo purpose, this is simply an address, not a multi-party computational. Then we have a mapping that will count the number of deposits that we have made, so we won't ever repeat the same deposit twice. Then we have asset ID to token address, which basically means we have in our own bridge, in our own system, we have asset IDs which are mapped to a token address, because we can end up with a token on Ethereum and a token on Polygon that doesn't have the same address. So we need a way to link them. That's why we have the asset ID. Then we have a burn list, which basically tells us who is the source bridge and who is the destination bridge, because the source bridge, the source chain and the destination chain, because the source chain is the one that holds the actual asset, the native asset, and the destination chain is the one that holds the fake asset. So this is how we know what do we have to do. Do we transfer or do we burn or mint? Then we have nonce. This is exactly the same as the nonce we have on Ethereum. So we are going to count on each chain on how many transactions we have so we don't repeat them. And then we have a modifier that is going to check whether the sender of the transaction is actually the multi-party computational address. And then we have two functions. The first one is walk. So walk will do two things. The first thing is going to check whether the token that we want to swap is part of the burn list. And if it's part of the burn list, it will burn the token. And if it's not part of the burn list, it will transfer from the user to the bridge itself, the amount that we want to swap. And it will do some sanity checks to check if the token address is valid, if the amount is valid, and so on and so on. And at the end, the most important is it will emit an event, and that event will be used by the external verifier to use it as an input for the transaction that the verifier is supposed to perform on the other chain. And then we have the execute method, and that method can only be called by the multi-party computational address. It will check whether the deposit was already processed or not. Again, it will do some sanity checks. It will mark the deposit as already used and processed. And again, it will check the burn list. If the token is part of the burn list, it will mint the token, which means that we are minting tokens against user walking the token on the first chain. And if it's not part of if it's not part of the burn list, it will transfer the token from the bridge to the user. And again, it will emit an event. So I have deployed the contracts on Goerli and Sepolia, okay, and I have them on Remix. Let me just turn on my internet. Okay, so my MetaMask is currently connected to Goerli, which is our source chain, which means that the Ether that is on Goerli is the original ETH, and we want to transfer it to Sepolia and get the representation of the Goerli ETH. So just to check. So we have two bridges. The first bridge is deployed on Goerli, and the second bridge is deployed on Sepolia. And here we are on the Goerli testnet. And now, yeah, I almost forgot the most important part, which is the actual verifier, the third-party verifier. It's written in JavaScript/TypeScript. It basically, the only thing that it does is listen for the deposit event that we're emitting whenever the user walks the funds, and do some sanity checks again, and execute the opposite transaction on the destination chain. In our case, the destination chain will be Sepolia, so we'll walk funds on Goerli, and the verifier will see that. It will see the destination chain, which is Sepolia, and will send the transaction to the Sepolia network bridge contract that we have. Okay, so it's started, and now we have to pass the destination chain ID, which for Sepolia is a huge number. I'm not sure if you see it. Okay. Then we have to set up to send the asset ID. In our case, the asset ID is basically 000, and it's linked to the DAI token on Goerli. And then we have to specify the recipient of the funds. The recipient of the funds will be seen by the observer or the verifier, and will send the funds to that address. And the amount is, yeah, obviously the amount. Okay, so I confirm the transaction. Then the verifier at some point is supposed to see that transaction and do the opposite, which is basically code a bridge on Sepolia, because the destination chain ID points to that network. And if we are lucky enough, okay, yes, so the deposit is received for that asset with asset ID 000. The user, my address, sends 100 units to my own address on the other on the other chain, from chain 5, which is Goerli, to chain 1111, which is Sepolia. And this is the execution transaction. Now, if we go to Sepolia and check that transaction, basically we have minted 100 units, which is 0.16 zeros and 1 Sepolia DAI. And our Goerli contract now should have the same amount, but in DAI, which is on Goerli. So yeah, that's pretty much it. Do you have any questions? Thanks. And the most important thing is that the verifier that executes the transaction on the other network must be some kind of multi-sig or some kind of network that makes it in a trustless way, because right now I have the complete power over the bridge and I can take all the assets basically. But yeah, if we all have the same, if we all share the same secret key and we act as a network, it will be, I guess, much more secure. Okay, if there are no questions, thanks again.